All right, now, since class got canceled today, we're going to do this lecture online instead of in class. And so we're going to start our conversation about chemical thermodynamics. So this is an introduction to chemical thermodynamics. Now, I want to warn you off the bat, this stuff is probably the most complicated part of this semester. It will get confusing. There's a lot of math involved and a lot of theory involved. I'll try to minimize the theory that's not important and maximize the theory that is important. All right, so here is what chemical thermodynamics is all about. It's really going to be crucial to understanding why phase transitions happen when they do. It's also going to be crucial to understanding how emissions form. So let me start off with just a little example which shows why we need chemical thermodynamics. Okay, so what I've just drawn for you is a chemical reaction, and it might look a little bit similar to the ones we did during combustion, except you should notice one key difference, which is that there is a nitrous oxide component right there. Now, you've done this before where you've had a chemical reaction, had to balance it and figure out the coefficients A, B, C, D, E, F in order to make all the atoms balance. So you have the same number of atoms of carbon on the left as you have on the right. What I'd like you to do is to take a second and actually pause the video and try to figure out how to balance this reaction. Figure out what those coefficients are. For real, like pause the video. Okay, you still probably didn't pause it, but I'm serious, like pause it, give it a try. All right, you probably still didn't pause it, but don't blame me when this concept doesn't become clear later. All right, this is what you should have found. You should have found that while you can calculate the coefficients for the carbon dioxide in the water, you can't calculate any of the other coefficients. And what chemical thermodynamics is going to do is it's going to be able to help us determine how to find those coefficients for this entire chemical reaction. Because what you actually have here is oxygen and nitrogen reacting to form nitrous oxide. And so what we're going to get to at the end of this section is we're going to be able to figure out, based on the chemical thermodynamics of that nitrogen and oxygen reaction, how much nitrous oxide we're going to have in the emissions. All right. And just for a quick point of relevance here, where nitrous oxide typically shows up is in high temperature combustion. And so that happens in diesel emissions as well as in coal emissions. All right. So we've talked about equilibrium in thermodynamics as being a combination of mechanical equilibrium and thermal equilibrium, right? Where mechanical equilibrium was this idea that you had pressures that weren't changing anymore. Thermal equilibrium is where temperatures aren't changing anymore. But there's really another form of equilibrium that we have to deal with, and that's chemical equilibrium, okay? And I'll also add in here that's also phase equilibrium. And so what that means is that when we're talking about equilibrium and when reactions hit equilibrium, we also need to consider when the chemical components stop changing, or in particular when the mixture of chemical components stops changing. And that also ties into phase equilibrium, which is, when does the liquid phase and the vapor phase even out? When do we have a stable quantity of vapor and a stable quantity of the liquid? And what this section is going to be all about is building the mathematics and the theory to be able to predict and understand when chemicals will stop changing, when reactions will stop shifting, as well as when phase stops changing as well. So for example, we've talked before about how you can calculate the quality of steam at a given temperature and pressure, or a given temperature and enthalpy or something like that. But we've never really talked about why that's the equilibrium point. And so one of the things that we'll get to derive here is when that equilibrium occurs between liquid and vapor. But the emphasis is really going to be on when an equilibrium occurs within a chemical reaction. And that becomes, again, particularly important for emissions. All right, so in order to talk about when equilibrium occurs, we're going to need to build some theory first. So this is going to get a little bit math intensive. There's going to be some differential equations, but you guys are grown up, so I'm going to hope that you can deal with it. So first equation that we're going to need to look at is that, remember that for a closed system, delta E equals Q in minus work out, okay? And so from that, assuming that kinetic and potential energy are stable, that means that on the left side, this is just going to be a change in internal energy. And if we turn that into a differential form, what that would say is that a differential change in internal energy is going to be caused by some minute amount of heat transfer minus some minute amount of work. Or to put slightly differently, if you put a little bit of heat and do a little bit of work on a system, that should result in a little bit of change in the internal energy. And recall as well that for a closed system, work is typically going to be boundary work. So this is really dq minus p dv, which is some differential amount of boundary work. All right, so that's the energy balance. Let's also look at an entropy balance on a closed system. So an entropy balance on a closed system says delta S equals integral dq over t plus sigma. Okay? If again we take this in a differential form, what we're going to find is that a differential change in entropy is going to be caused by a differential amount of heat transfer, which means we can drop the integral. So that's just going to be delta q over t plus some differential amount of entropy generation. Now, if we solve for dq on both equations, then we're going to find the following. All right, so solving for those two equations. From the first equation, dq equals du plus pdv. From the other equation, it equals TdS minus Td sigma. Those two have to be equal to each other because they're both del Q. So combining those two equations, what you end up with is that TdS minus du minus pdv is equal to T sigma. Okay? So if TdS minus du minus pdv equals T sigma, then that means that this has to be greater than or equal to 0. So what that means is if there's any thermodynamic process, anything that's happening, temperature times the change in entropy minus the change in internal energy minus pressure times the change in volume, all of that has to add up to something greater than or equal to 0. And this equation here, the greater than or equal to 0 one, we're going to call this equation 1, and we're going to come back to that a little bit later. So let's do a little thought experiment about this equation real quick to see if we understand what it's saying. So let's imagine that you have a closed system. Imagine that it's a rigid vessel, and imagine that it's insulated. And imagine that there's some liquid in here, and also some vapor. Okay, so liquid water and steam, for example. Okay. And let's imagine that what this system is trying to do is it's trying to figure out how much should be liquid and how much should be vapor. All right, so this is a thermodynamic process. We're trying to find where the equilibrium is going to occur between the liquid phase and the vapor phase. Well, let's look at this equation real quick and see what it says. In this case, if it's insulated and it's rigid, what's du going to be? Well, that's going to be 0 because there's no heat transfer into or out of the vessel, so there's nothing to change the internal energy. dV is also going to be 0 because it's a rigid tank. And so what this eventually says, if you think about it, is this means that the change in entropy has to be greater than or equal to 0 as this thing finds its equilibrium, as we find an equilibrium between the liquid phase and the vapor phase. So what that means is that vapor will form until entropy hits some maximum value. Okay, so that means that as this equilibrium is happening, as the liquid and vapor are trying to figure out where they're going to be in this phase equilibrium, what's going to happen is that the system will continue to change in a way that causes the entropy to rise until the entropy stops rising. And once it hits that maximum value, that's where the stable equilibrium is going to happen, because that's the point when this equation will stop being greater than or equal to 0. Okay, so this equation said this is what happens. This is what must happen in the relationship between entropy, internal energy, and changes in volume. All right. It always has to be greater than or equal to 0. In this specific case, it said the entropy has to be greater than or equal to 0. So as the equilibrium is forming between the vapor and liquid, it's going to change in such a way that changes in entropy are going to be positive, or entropy is going to rise until it hits a stable maximum point. That stable maximum point is going to be the quality that this is going to exist at in a stable equilibrium. Remember, this chapter is about understanding why that equilibrium occurs. You've already dealt with that equilibrium. You've already been able to calculate for the quality. You've already done that thing. But you've never really thought through, why does the quality have to be what it is? Why does the equilibrium have to exist where it exists between the vapor and the liquid? And so what this chapter is going to do is give us the theoretical foundation to understand why the quality is what it is and why that equilibrium occurs when it does. So what this means, just to put it in writing, is that the quality must be the value such that the entropy is at its maximum possible value. That's what the quality will be. That's what the stable quality will be. All right, moving on. Let's remind you of something. So recall, enthalpy was defined as internal energy plus pressure times volume. Okay, so it's just a combination of properties. If you know internal energy, you know pressure, you know volume, you can add up internal energy plus the product of pressure and volume. That's what enthalpy is. And so the reason that we calculate enthalpy is that this just ends up being a useful term because it shows up a lot in energy equations. We oftentimes will see this U plus PV term. And so rather than calculating that separately 100 times, let's just make a column for it and calculate it all at once. That's what enthalpy is, and that's why we use it. It's nothing fancy about it. If you want, you can always go into the tables in the back of the book and you can look up U, and you can look up pressure, and you can look up volume, and you can add up U plus pressure times volume, and every time you will get the value for enthalpy. So that's all it is. Not very complicated. What we're going to do now is we're going to introduce another combination that proves useful. And so we're going to call this one G. And this is the Gibbs energy. Gibbs was a guy who was like one of the fathers of thermodynamics. All right. So the Gibbs energy G is equal to enthalpy minus the product of temperature and entropy. Okay, so in the same sense that enthalpy is just a combination of other properties, Gibbs energy is also a combination of other properties. You can look up enthalpy, you can look up temperature, you can look up entropy, and you can take enthalpy minus the product of temperature and entropy. Not super complicated. And this is going to prove useful for various reasons. All right, so let's look at why Gibbs energy proves useful. First, let's substitute in U plus PV for the enthalpy. All right, substituting for enthalpy, we get this equation here, U plus PV minus TS. Now what we're going to do is we're going to take a differential on it, and if you take the differential, we're going to get the following. Okay, so the differential change in Gibbs energy is equal to some differential change in internal energy, plus the differential change in the pressure volume product minus the differential change in the temperature entropy product. Now, when we take derivatives, we have to use the product rule. Remember, UV prime equals U prime V plus UV prime. So doing that, we're going to get the following expression. All right, so now we have this expression where the differential for pressure and volume turned into PdV plus VdP. Temperature times entropy was TdS minus SdT. Now what we're going to do is we're just going to do a little bit of rearranging, and we'll show you what we end up with. All right, so all I did was rearrange stuff and put things on different sides of the equation. And notice here on the right side, what I did is I kept the terms TdS from here, and du from here, and PdV from here. And notice that these are the same combination of terms as we had up here, TdS minus du minus PdV. And we knew that that combination of terms had to be greater than or equal to 0. TdS minus du minus PdV. That's what we have right here, TdS minus du minus PdV. So that means we know that this combination of terms here has to be greater than or equal to 0. So what that means is that if we have a reaction that's in mechanical and thermal equilibrium, Well, what's the definition of mechanical and thermal equilibrium? That means that there's no change in pressure and there's no change in temperature. So those have to be equal to 0. dP and dt have to be equal to 0. So if those are equal to 0, then what that says is that changes in the Gibbs energy have to be less than or equal to 0. And the reason it's less than is that there was this negative sign right here. Okay? So when you have a reaction in mechanical and thermal equilibrium, what this means is that the reaction will occur in such a way that it finds a minimum in the Gibbs energy. Okay? So the Gibbs energy is always going to go to the minimum. All right? So as a chemical reaction is occurring and the products are forming and reactants are reacting and the reaction is going back and forth, for example, nitrous oxides and nitrogen and oxygen, or OH and hydrogen and water, as those reactions are occurring, where they're going to find a stable equilibrium is the point at which the Gibbs energy is at a minimum. Okay? And if you don't understand that, if that doesn't make sense, you should go back and rewatch this again, because this is pretty critical to understanding here. The Gibbs energy minimization is how all reactions occur, whether it's a phase equilibrium or a chemical equilibrium. If you have something that's in mechanical and thermal equilibrium, so pressure and temperature are constant, when you're trying to figure out within this mechanical and thermal equilibrium, when you're trying to figure out what the chemical equilibrium is going to be, when you're trying to figure out what reactive species are going to form and stably exist, if you're trying to figure out what's going to be the balance between liquid and vapor in a phase transition, it's going to be the point where the Gibbs energy is at a minimum. Okay? All right, so this idea of minimizing the Gibbs energy, this is important for several reasons. First reason, the Gibbs energy dictates everything. Everything. All chemical reactions, all chemical processes, everything are trying to minimize their Gibbs energy. Why does a chemical reaction occur? Because it's trying to minimize its Gibbs energy. All chemical reactions at all times, whether they're chemical reactions in our body or the chemical reactions associated with combustion, the reason that a chemical reaction occurs is that it is trying to minimize its Gibbs energy. The entire forces of nature are always trying to minimize the Gibbs energy. All right, another reason that it's important. Turns out it's actually really important for nanotechnology. So I did my PhD in nanotechnology, and we talked about the Gibbs energy a lot, in particular because there were a lot of reactions at the nanoscale that work differently than reactions in larger scales. And it all comes down to differences between the Gibbs energy and the enthalpy. So there's a reaction that might occur one way at the macro scale because of it's driven by enthalpy related reasons, and it might occur totally differently at the nanoscale because the way the mathematics work, it turns out that the Gibbs energy does something a little bit different. In particular, this thing called the surface energy, which is accounted for in the Gibbs energy, becomes extremely important as well, because the surface becomes a relatively larger part of the system when you get smaller and smaller and smaller. If you think about it, every time you cut an object in half, you expose a new surface, and so the surface to volume ratio keeps going up as you get smaller and smaller and smaller. And that becomes extremely important in nanoscale situations, and so there are a lot of reactions that occur differently in the nanoscale. All right, third reason that this is important. It's important for understanding phase equilibrium. When do things stop forming liquids and start forming vapors? When do things go from the solid to the vapor phase and sublimate? How do phase transitions occur and why do they occur? Well, equilibrium occurs when the change in Gibbs energy associated with a reaction or with an occurrence is equal to 0. Okay, when the Gibbs energy change is equal to 0, which is the same thing as saying when the Gibbs energy is minimized, okay, the derivative will be equal to 0. When the change in Gibbs energy is equal to 0, that's when phase equilibrium happens. So in particular, if you're thinking about a liquid to volume transition, that's going to be when the Gibbs energy of the liquid is equal to the Gibbs energy of the vapor phase. And this is what we call the criterion for equilibrium. Okay, whether it's a phase equilibrium or a chemical equilibrium, the criterion is when the Gibbs energy stops changing. When the Gibbs energy hits its minimum, that's when you get equilibrium to occur. All right, let's make another note now. This is going to be about how properties are calculated. And I know this all seems really abstract right now. I promise you what we're going to get to is what we started with. Remember, we wrote that equation with the nitrous oxide, and we said, hey, we can't balance this. Where we're going to get to eventually is going to be able to balance that using the Gibbs energy and some relations related to the Gibbs energy. So just stick with me, and eventually this will all come together. But before it can come together, I've got to introduce all this vocabulary first. All right, so another note. First of all, recall that any intensive property, remember intensive means independent of size. So any intensive property is a function of two properties. Okay, remember if we look up 2, we can always find the thirds or all the others. Okay, so any intensive property is a function of only 2 properties. You give me 2, I can get any other intensive property. And recall as well, an extensive property is one where the size does matter, okay, where the quantity matters. All right, so for an extensive property is going to be a function of 2 properties as well as the quantity. All right. So if the Gibbs energy is equal to H minus Ts, all right, so that's big G is big H minus T times big S, okay? H is a function of 2 properties and quantity. Minus Ts, and both temperature and entropy are a function of 2 properties, and entropy is also a function of quantity. So that means that G is also a function of 2 properties and the quantity. Okay, so what that means is that if you have 2 properties and the quantity, you can get G just like you can get any other property. Now, for mathematical reasons, we're typically going to choose the 2 properties for the expressions of G to be temperature and pressure. Okay, technically it could be any 2 properties, but the way the equations play out, it makes most sense to use temperature and pressure as the functions for G. And then for quantity, we're going to use moles. But where this gets a little bit more complicated is that what if you have multiple components, all right? So when you're looking at a reaction, you're not just looking at the Gibbs energy of one thing, you're looking at the Gibbs energy of all the components in the reaction, all the reactants and all the products. So this quantity is actually going to be a little bit more complicated than just a single value for N. Instead, you're going to get something like the following. So the Gibbs energy is going to be a function of temperature and pressure and the molar quantities of all the components in the mixture. And the reason the molar quantities are particularly important is that recall that the partial pressure of a given component in a gas mixture is going to be the mole fraction times the total pressure. So you're going to need all the partial pressures in order to have 2 properties for every component, or you need the total pressure and the moles for all the components in order to get the partial pressure. So either way, you're going to need molar components for everything in the mixture, as well as the pressure, as well as the temperature. Conceptually, you can also think of it this way. You can also think of it as though there's a specific Gibbs energy for each component, which is going to be a function of the temperature and pressure of that component. And then the total Gibbs energy of that component is going to be the moles of that component times the specific, I guess I should draw a line over the top, molar Gibbs energy, okay? And then the Gibbs energy of the mixture is going to be some combination of the Gibbs energy of each of the components. All right, now, hopefully that all made sense. If it didn't, please go back and rewatch. And I should apologize for the poor handwriting. It's a little bit tricky to write on a tablet as opposed to a whiteboard, but hopefully you can read it as I talk through it. All right, so one last thing. There's a long derivation that I really don't want to go into because it takes a lot of time and it's mostly confusing. But the short version is the following. All right, so you can show that the Gibbs energy is the sum of the molar quantities times the derivative of Gibbs energy with respect to the moles when held at constant temperature, constant pressure, and all the other components being constant. All right, that might not make any sense, so let's try and take it piece by piece. What it's saying is that hopefully this part in here at least will make some intuitive sense. So if you have an understanding of how Gibbs energy changes with quantity, and you multiply that change by the quantity, this is just like multiplying a derivative by like rise over run times the run, okay? So if you know how it changes with quantity, you multiply it by the quantity, that's going to give you the amount of Gibbs energy due to this component in the mixture. And the summation is saying, let's sum it up over all the component in the mixture. So from I equals 1 to j, where j is the total number of components in the mixture. So if there's 5 things in the mixture, there'd be 5 terms in this summation, okay? So what it's saying is that for each component, you take the quantity of that component, multiply it by how the Gibbs energy relates to the quantity, and that gives you the Gibbs energy of that component. You add all that up, and that gives you the Gibbs energy of the mixture, right? Now, what this piece over here is saying is that when you're taking a partial derivative, if Gibbs energy depends on temperature and pressure and the quantities of all the things in the mixture, when you take a partial derivative, you have to hold everything else constant when you take that derivative. Okay, so this is saying hold the temperature constant, hold the pressure constant, hold all the components constant, and see just how the Gibbs energy changes with this one component. Okay, that's what this notation means. N sub L would be all the components that are not component I, because component I is the one that is changing, and we're trying to figure out in this derivative how Gibbs energy changes with this component I. All right. If this doesn't make any sense to you, don't worry about it too much. This is the mathematical notation that you use for partial derivatives because you can't take a derivative of just one thing when there's multiple variables in there. You have to assume the other variables are constant, and this is just saying assume everything else is constant except for n sub I. All right, so you're taking quantity, multiplying it by how energy changes with quantity. That gives you the energy of this component. You add up the energy of all the components. That gives you the Gibbs energy. All right, this term here, the derivative of Gibbs energy with respect to quantity, this is what we call the chemical potential. And we give it the symbol mu sub I. All right. Now, hopefully at this point you're looking at this and you're just confused as hell and you're like, how am I supposed to figure out any of this stuff? Okay. What it's going to come down to is that it turns out that we can evaluate the chemical potential for a few specific circumstances. And those few specific circumstances are going to prove to be fairly useful for a handful of different things. So if you hang with me, I promise you we're going to get to a point where we're going to calculate this chemical potential and we're going to use it to calculate some useful things. And that's going to happen only in a couple of specific circumstances. All right, so just before we finish up here, let's do one quick little example of how this ends up saying something useful, okay? So recall that for chemical equilibrium to occur, the change in Gibbs energy has to equal 0. That's when chemical equilibrium occurs. So if the change in Gibbs energy is 0, then that means that the sum from I equals 1 to I equals j of mu sub I times dn sub I has to be 0. Okay, so why does that need to be the case? Well, if we take the differential up here, dg, then we have to take differential on the right. If we take differential on the right, we're looking at how Gibbs energy changes with quantity. So if you have a differential change in the quantity of something, that's going to cause a differential change in the Gibbs energy. So if the differential change in the Gibbs energy is 0, then summing up the differential changes in each of the quantities times the chemical potential should add up to 0 when we're in equilibrium. Okay? So to put it slightly differently, I guess I can also write this, which is to say that if we take the differential of Gibbs energy, dg, that's going to be the sum from I equals 1 to j of dn I times mu sub I, where we're just substituting mu sub I for the chemical potential here. We're taking the differential of g, which gives us a differential change in quantity of each species. Okay? So if in equilibrium dg equals 0, so maybe I'll write that explicitly in equilibrium, then equilibrium will occur when mu sub I times dn sub I equals 0. So let's do a quick, simple application of this to phase change. So in a phase change, how many components do you have? Like let's say a liquid to vapor phase transition. Well, you'd have two components, the liquid and the vapor. Okay, so our summation is going to have two terms because there's two components. And what that's going to say is that 0 has to equal the sum of mu sub I times dn sub I. So if we have liquid and vapor, that's going to be mu sub L times dn of L plus mu sub V times dn sub V. Okay? So those are the two terms. They have to add up to 0. And we know that if we have some liquid forming or some vapor forming, the change in the amount of liquid has to be negative the change in the amount of vapor, right? Because every little bit of liquid had to come from the vapor phase. So if you get condensation, the amount of liquid goes up and the amount of vapor goes down. And they have to be negative the other because all the liquid comes from the vapor. So if I get 3 more atoms of liquid, that means I have 3 less atoms of vapor, okay? So if dnL equals negative dnV, then what this says is that if I substitute this into this equation here, what this says is that mu sub L has to equal mu sub V. Okay, so chemical equilibrium occurs in a phase transition when the chemical potential of the liquid and the chemical potential of the vapor are equal to each other. Okay? Now we haven't actually talked about how to calculate the chemical potential yet. Don't worry about that yet. But this is just to show one example with two components in a phase transition. All right. So that's all I wanted to cover today. I know this is probably super confusing. There's a lot of stuff here. Please rewatch this video if you need to rewatch it. The really important thing here is just to get a grasp on the vocabulary more than anything, okay? Because we're going to deal with the chemical potential, and so when you talk about the chemical potential, you need to know what we're referring to. We're going to talk about the Gibbs energy. When we talk about the Gibbs energy, you need to know what we're referring to, okay? And if it's still confusing right now, that's fine. The key thing here is to understand that we're going to get a couple of specific applications. We're going to calculate some things that are going to be very useful. But in order to do those things, you need to understand what the chemical potential is, and you need to understand what the Gibbs energy is, and you need to understand that the Gibbs energy finds its minimum in chemical equilibriums, and the change in chemical energy when you're in chemical equilibrium is equal to 0. Okay, so those last few things I just mentioned, if those are confusing to you, you need to rewatch this video because those are the crucial concepts that are important to understand. All right, we'll be back in class on Thursday, and hopefully we'll be able to pick up some questions then.